In this first example, I will begin by writing a program entirely from ones and zeros, and then go back and deconstruct or manually decompile the binary file into an assembly program. So to begin, let's open our command prompt. Hang on. First, let me get my path. I'm going to go to assembly. I want to be here. Copy that. Copy 10.4. CD. Paste. Good to go. All right. I'm going to be using the test file as usual. I want a bootloader to begin with. Let me just go copy my magic M tab to T tab. Put that magic number right in there. Oh, I do that all the time. COPY. Y and T are close together, but that's not forgiving it. M tab, T tab. Overwrite, yes, indulge me. Thank you. Good to go. So if I have a look at T tab now, there is our magic number expressed in hexadecimal. We want to express it in binary. Okay, class, what is the magic number expressed in binary? Who can tell me, huh? Good. 01, 01, 01, 01. B for binary. And on the next line, of course, 10101010 in binary, and that should be good to go. Just for the heck of it, let's type our list of shortcuts. I'm just gonna grab that, copy paste, and then grab that, copy paste, and B tab. There, run our binary. Okay, good to go. It is booting, which I didn't see any reason there should have been a problem, but you know. All right, back to our actual program. Let's write some code in there, and we're going to do it using all ones and zeros. Let's write some data bytes. So we'll start with 1011. Followed by 1000 binary, and 11 in binary. We know that to be 2 plus 1 is 3. Followed by 1001 in binary, which is what? 8 plus 1 is 9. Okay. I'm just going to plow ahead and go ahead and write some mystery numbers in here, and then I'll go back and add the comments and all that. 1011 followed by 1011. Oh, really? Okay. Binary, and that'll be 1 to 4, followed by null. And I don't have to say 0 in binary because it's universal, really. DB 1011. Noting any similarities here, followed by 1001. So technically, this value and this value are next to each other in memory. We are calling commands to the directives to the processor, followed by some data, command, data, and all of these three commands are very close to one another. In fact, this one, as you can see, all of the preceding numbers are identical on all three of these except for the last 2 digits. This one starts at 0. This is the next one in line, and this one comes a couple after that. You know, these are again various direct commands to the processor. You know, so the assembler is going to, well, the processor itself, I'm sorry, is going to expect a command followed by some data, and that data could be the same number value, even, just depends on the order in which the processor receives them and what it interprets them as. Okay, so I was nearly complete here, and I got all sidetracked. 1, 0. Speaking of ones and zeros, same with the 1. 1 and 0 are the same whether you're speaking in binary, hexadecimal, or whatever. Once you get to 2, then it's different in binaries, but 0 and 1, we can just write it as a decimal value. If you want to be like consistent, you could say binary, but it's all going to be the same to the processor when it receives that. Okay, we've sent 3 directives to put some values in registers so far. Now we will do something with that, with those values. 1, 1, 0, 0, a little bit different place in memory. 1, 1, 0, 1, binary. 1, 0, 0, 0, 0. I forgot the comma apparently. There. Okay, let me just save all that. If I missed any, I missed a binary. I have to specify that it's not 10,000. It is 1, 2, 4, 8. It is 16 in binary. Okay. Make sure that that is saved. Good to go. I'm going to head over here. And if I up arrow 2 times, there's NASM. Down arrow 1 time. There we go. We have our beating heart. The computer loves 1s and 0s. That's all it understands, technically. All right. So you may go to other programs or stick around and we will decompile this. Okay.